So today we are presenting the MiniRAG paper, and the authors have, the major challenges of using the ROG system in large language model was that it was not that effective in using the same ROG system from large language model to small language models. So the authors have proposed this paper to tackle the challenges of using the ROG system in small language models, which were previously using the large language models. So before diving into the main paper, I would like to give a short introduction about what is ROG. Next slide. Okay, RAG, also which is called Retrieval-Augmented Generation. So, is a technique in AI that enhances the, the, the response or the generation of the large language model by integrating the relevant information from external databases. This process mainly involves three main components, and that is indexing and retrieval and generation. So the indexing is converting data into searchable representation, and retrieval is about fetching the data, fetching this data by using the user query, and the final generation is about generating the output based on by combining the retrieved data along with the model's own information. And the key approaches for the database construction in RAG are chunk-based method and graph-based method. In chunk-based method, the text data or the document is divided into small chunks, and during retrieval, the relevant chunks are retrieved based on the similarity. And the graph-based method organizes the information into the knowledge graph, and retrieval is done using the graph traversal or link-based management system. Next slide. And current RAG systems heavily rely on large language models. The LLMs provide high performance, but they come with substantial computational overhead and resource requirements. This means it is difficult to deploy them on resource-limited environments. And the small language models, on the other hand, offer advantages in terms of computational efficiency and deployment flexibility. However, they struggle with key RAG operations like semantic understanding and information retrieval. The existing RAG architectures designed for large language models often fail with small language models, leading to performance degradation or even system failures. So this existing this mismatch shows that there is a critical need for RAG systems that work effectively with small language models. Next slide. Sorry. To address these challenges, the authors propose a MiniRAG, which is a novel RAG system designed for simplicity and efficiency, especially for the using the small language models. Design of the MiniRAG is based on three key observations. The first one is about pattern matching and localized text processing. The small language models struggle with sophisticated semantic understanding, but they do excel at pattern matching and localized text processing. And the explicit structural information can compensate for limited semantic understanding. And finally, the complex RAG operations can be decomposed into simpler, well-defined steps to maintain the system robustness without requiring any advanced reasoning. And based on these observations, MiniRAG prioritizes the structural knowledge representation over complex semantic understanding. Additionally, it leverages it is a graph-based patterns that suit the SLMs strength. Next slide. MiniRAG incorporates two key technical innovations. The first one is semantic-aware heterogeneous graph indexing, which combines the text chunks and link entities, and it reduces the reliance on complex semantic understanding. And the second one is the lightweight topology-enhanced retrieval, which uses the graph structure and heuristic search patterns for efficient knowledge discovery. It does not require advanced language capabilities and reduces the use for complex semantic matching. And these These innovations allow the MiniRAG to achieve 1.3 to 2.5 times higher effectiveness than existing ROG systems while using only 25% of the storage space. And furthermore, it shows strong robustness in transitioning from the large language models to small language models with accuracy loss of just 0.8 to 20% across different scenarios. So next slide, and I think our team is going to continue from here.
Yeah, so I'll be taking over from here. So as Depeche sort of already talked about, the small language models are pretty limited in their semantic understanding abilities. And this makes RAG incorporation difficult because that's really what's required when like a standard chunk-based RAG is used to improve a prompt to either incorporate external information or to excuse me, or to provide further context to the large language model to give essentially better answers to its queries. And because of this, basically this limitation in semantic understanding for language models, their answers are also usually much more vague than what you would anticipate from a large language model, especially when you're able to do RAG incorporations. So to the authors of MiniRAG directly, there we go. The authors of MiniRAG directly structured their graph to address these challenges in particular. And they did this by structuring the graph part of MiniRAG into what's called a semantic-aware heterogeneous graph. What that really means is that the semantic relationships that are associated with text documents are expressed essentially explicitly in the graph itself, in the structure of the graph. And the heterogeneous part is referencing to the fact that there are two generic node types in the graph. There are text chunk nodes, which are actual, well, chunks of whatever sort of document text is being incorporated. You can think of these as paragraphs, essentially, if you're getting, like, say, a report is the underlying document, and then entity nodes, which represent like key elements, key semantic elements, key elements that need to be understood for the RAG itself. So these can be locations, they can be events, they can be people, they can be ideas like, say, some of the different entities are restaurants, it might be food items, things like that. And then the between these nodes are then edges or connections, and these will take one of two types as well, either entity-entity connections, which capture the actual semantic relationship between two nodes. So you can, in this instance, you can think of this as, say, you have two location nodes, maybe they're listing two restaurants. This might include information about, say, the distance between these two, like the spatial distance between these two restaurants, but also whether or not in the documents themselves there's been like a hierarchy established. One restaurant is better than the other, say. While the entity chunk connections essentially indicate from what chunks different entities are sourced. So if you have a paragraph that mentions one restaurant, that would link back to that chunk node there, and different ones for different named entities. These different, in order to really make that that offloading of semantic understanding more robust for the SLM, those different types of connections are then further enhanced by deeper descriptions, essentially, of the different types of relationships that exist here. So either either a description of essentially where in the document or how in the document an entity node is sourced for those entity chunk connections, and then very explicit relationship contextualization for the entity-entity edges. All of this allows for, essentially allows for the RAG of MiniRAG to become much more of a pattern, a graph pattern recognition problem, as opposed to a semantic understanding problem. And these are much simpler problems ultimately for SLMs to understand because they are excuse me, they are essentially are able to identify, say, what the best, the shortest path between two nodes in a normal relationship is, or different connectivity type metrics, things like that. And the because they are able to recognize this, if you turn the problem of retrieving essentially the most important information in order to augment a prompt into one where it's simply recognizing the best paths between different entities, the SLM is much better suited to being able to do that problem and is actually able to get the information it needs to provide much more meaningful answers to queries it's handed. So the steps to do that, the authors of the paper make the steps of that retrieval process very explicit. The first step is a query will be passed to the SLM, and the SLM will perform a first step identification of the relevant entities in that query that can be mapped to nodes in the graph, and will also predict essentially potential answer nodes from that query. So in this instance, say the query is asking for, is essentially asking for a restaurant, the predicted answer types would be restaurant type nodes, information based on that. And this then gives the SLM the ability to identify actual paths between what it considers as starting point nodes, those entities from the query that it identified, and its predicted answer types. And it can perform fairly straightforward analysis on what the shortest paths are between the candidate starting points and the candidate answer nodes, and also determine connectivity metrics specifically associated with the starting point nodes in order to determine what is essentially what is the most likely starting point for a good answer. The thought there being that the more paths, the more reasoning paths that a starting point node is associated with, the more likely that starting point node is to be a good place to start on reasoning. Those metrics, which are topologic in nature, they're basically graph metrics, are then combined with similarity analysis that is performed, cosine similarity analysis that's performed on the actual text information from the chunk nodes that are associated with all of those entities and the different candidate reasoning paths. And that is collectively used to rank the different reasoning paths and contextual information of the text chunks, and finally to select what are going to be either your topmost reasoning path or at least the K top reasoning paths. Those then can be incorporated, specifically the textual information of the chunk nodes and the semantic information of the semantic information of the entity edge information is incorporated into the actual prompt in order to really augment it and provide the needed context and the needed semantic understanding for the SLM to function. Munam, your mic's on. Can you mute yourself, please? With that, we move on to the evaluation metric, and I believe that Olwyn will now be presenting.
Initially, our focus wasn't just on the numbers. We wanted to understand how the actual implication does. Is MiniRAG really a game changer, or its improvement is just marginal? And what makes it different from the existing RAG models, and can its optimization be applied any elsewhere. So we broke the evaluation into three key areas, mirroring the structure of the research paper while adding our own observation. So first research question is the comparative performance. Does MiniRAG actually outperform the existing RAGs? If so, by how much? Second, component breakdown, which features to contribute most to its efficiency. Are all the components equally important? And third is the case study, which does the handle the real world retrieval task compared to the light rack. Next slide, please. Next slide. Okay, thank you. So imagine that an AI assistant on a phone that helps answer questions, summarize your notes, or even retrieve any past conversations. This is what an RAG is all about. So what about the challenges? Small devices don't have the same power as the cloud-based models. So we have to evaluate how well these models work under these constraints. So to do this, we use two data sets. First is the Lihua world. Think of this as the data set, which is filled with personal conversations, work chats, and social interactions. So basically, it tests how well the AI remembers and fetches the relevant past information. Second is the multi-hop RAG. It's more like a fact-checking assistant. So it needs to collect the information from the multiple sources, similar to how journalists verify facts across the different articles. Next slide, please. Next slide. Thank you. So the question is, how do we measure this RAG model if it's doing a great job? So you're using accuracy and the error rate. Accuracy tells us how often the model gets the right information, and the error rate tells us how often the model gets things which are completely wrong. So we tested with different models. Some are like GPT-4 Mini, which have the more power, but it needs more storage. Others are like Mini LM L6v2 and 3.5 Mini Instruct, which are lightweight, but it might struggle with the accuracy. Next slide, please. Next slide.
I've changed it on my end.
Okay. So talking about the numbers from the chart, for the Lua World dataset, which is the chat-based dataset, as you can see, the MiniRAG with GPT-4 Mini performed the best. It had 54 accuracy percent and only 19.44 error rate. And but when we change to a smaller model, the light rate dropped from 56 to just 35% accuracy. So that's, as you can see, that's a very huge drop. It means that light rate really relies heavily on the large models to function well. And interestingly, 3.5 mini instruct did okay with 53.29 accuracy, but its error rate was also higher at 23.35%. So it made more mistakes, but not as much as the light rag. For multi-hop rag, which is the checking data set. Next slide, please. So for multi-hop rag, MiniRAG again came up on top with 68.43 accuracy, meaning it retrieved the correct information almost 7 items times out of 10. And LightRag, on the other hand, dropped from 64.91, which is the large language model to 27.3, which is the small language model. And that is less than 3 correct answers out of 10 when using a smaller model. So clearly, LightRag is struggling with smaller AI models. So what do these results tell us? So LightRag really depends on the large models, making it less practical for an on-device. And MiniRAG is more adaptable and it works better for small devices. Next slide, please. So coming to the storage versus accuracy trade-off, this part is crucial because if an AI model is accurate, but if it takes up too much space, so it's useless for the small devices. So judging from the graph, we can note that MiniRAG is the best balance between the higher accuracy and lower storage usage compared to the traditional RAG. And the reason MiniRAG works well is that it optimizes how it stores and it retrieves information, so it reduces the need for the massive storage. For example, if you're trying to find a specific message in a chat history, so a bad AI model would read every single message, which would take forever. And a good model like MinRAG would index the key conversations and fetch only the relevant parts quickly. So that's the reason why MinRAG maintains accuracy without needing the tons of storage. Uh, the next step will be followed by Diana.
Okay, so what the authors did was like they carried out a study to fusions of key MiniRAG components through two primary experimental variations. The first experimental variation was they replaced MiniRAG's heterogeneous graph indexing with a description-based indexing approach, which requires comprehensive semantic understanding for generating accurate entity and edge descriptions. And the second experimental variation was they selectively deactivated specific modules during graph retrieval to gain insights into how each component contributes to MiniRAG's overall performance. Next slide, please. So one key finding was that the performance was deteriorated when streamlined indexing method was replaced with text semantic-driven indexing techniques. This finding validated the hypothesis about small language models and their limitations. And their limitations are actually the constraints in comprehensive semantic understanding, which actually impacts generation of complex knowledge graphs with entity relationships and the creation of comprehensive text descriptions. Another key finding was that the system performance was impacted when either edge information or chunk nodes was removed. And these elements facilitate effective query matching through query-guided reasoning path discovery, while compensating for the limitations of small language models during the data indexing phase. Next slide, please. So here we're showing how the accuracy and error rates were impacted when semantic-driven indexing removal was in effect. So actually, semantic-driven indexing removal causes the sharpest accuracy drop from 53.29% to 26.02%. If using Phi 3.5 mini instruct model. And similar, you can see the similar trends across all of the models. Next slide, please. And again, here, when chunk nodes were removed, the accuracy was slightly lowered, but still maintains competitive performance. You can see that the accuracy went from 53.29% to 48.90% in the chunk minus R chunk colon. This shows that the MiniRAG is designed to be efficient while retaining its accuracy. And next slide, please. And here, in this slide, we can see that the edge removal actually results in moderate accuracy degradation, but it still outperforms the other models, proving that graph connectivity strengthens retrieval quality. And you can see this trend across all models. Next slide, please. So MiniRAG's advantages were further demonstrated through a case study with LightRAG. Query-guided reasoning approach and heterogeneous graph indexing could handle multi-constraint queries effectively while overcoming limitations of small language models. Furthermore, LightRAG struggled with this task due to the limitations of its small language model and the small language model's constraints in extracting appropriate high-level information and the noise in the graph-based index actually led to ineffective direct embedding matching, and thus resulted in less accurate answer retrieval. Next slide, please. And on the other hand, MiniRAG's query-guided reasoning path discovery mechanism enabled precise and relevant knowledge retrieval. MiniRAG constructed query-relevant knowledge paths by leveraging its heterogeneous graph indexing structure. And the structured reasoning approach and strategic decomposition of query elements allowed MiniRAG to navigate the knowledge space efficiently. Next slide, please. So in conclusion, the authors concluded that MiniRAG was presented as a novel RAG system to address the limitations of small language models in the existing retrieval-augmented generation frameworks. MiniRAG's heterogeneous graph indexing and lightweight heuristic retrieval mechanisms can combine text-based and graph-based RAG approaches while reducing the demands on language model capabilities. In addition, MiniRAG can achieve a performance as good as that of large language model-based methods, even when using small language models. And they felt that this is an important step toward enabling private, efficient, and effective on-device RAG systems. It also opens new possibilities for edge device AI applications.